What if a city once stood where you're sitting now? Glass towers, humming rails, neon veins of traffic and time erased it so completely that not a single brick remains. We like to think ruins last. We visit pyramids, temples, and shipwrecks, and assume that permanence is the rule. But geology is less a museum than a shredder. The planet is a patient recycler. Wind grinds, water dissolves, microbes digest, continents collide, and the seafloor itself dives back into the mantle. Most oceanic crust, the largest archive of Earth's surface, is younger than about 200 million years. Anything older is either gone or preserved only as rare scraps welded to continents. If an industrial civilization had risen 10 million, 50 million, or 100 million years ago, how much of its world would still be visible to us now? Close your eyes and imagine a metropolis at its peak. Steel frameworks climbing through cloud, data centers exhaling heat, chemical plants distilling new matter out of ancient oil. Then drop a curtain of time, first decades, then millennia, then millions of years. Buildings collapse, rebar rusts, concrete fractures, and melts into gravel. Suburbs sink beneath rivers that meander and cut new channels. Forests retake parking lots and prize them into loam. Climate swings fold and fault the landscape. Now add plate tectonics, the slow conveyor belt that drags ocean floor into trenches. Whole coastlines are chewed under and remade. The longer you run the tape, the smoother the world becomes. Cities don't turn into monuments. They turn into dust, and the dust gets buried, cooked, and recycled. That's the unsettling kernel of our question. If we vanished, what would remain? And could anything similar have come and gone before us? In science fiction, this idea is familiar. Lost empires beneath Antarctic ice, ruins under the Sahara, artifacts on the moon. But in real science, it has a name and a testable frame. The Silurian Hypothesis, proposed by NASA's Gavin Schmidt and astrophysicist Adam Frank, it asks a deceptively simple question. Would it be possible to detect an industrial civilization in Earth's geological record? Not, did one exist, but what would prove it if it had? The power of the idea is that it moves the conversation from rumor to evidence, from maybe to measure. Okay, suppose we look for ruins. That's our first mistake. Stone structures erode in tens of thousands of years, metals corrode even faster, and anything on the seafloor is on borrowed time. The Earth doesn't keep monuments well. What it keeps, if we know where to look, are signals. Chemical fingerprints in mud and rock, abrupt shifts in isotopes, oddities in the fossil record, layers of ash and silt that whisper a story written grain by grain. Think less Atlantis and more thin black line of soot or a spike in plutonium. Evidence? Yes, but not the kind you can walk through, the kind you have to tease out of cores and spectra. Now flip the lens onto us. If a future geologist drilled through sediments from our era, what would they find? They might not find a single recognizable building, but they would find a bundle of strange, global clues. Plastics that don't belong in ancient mud, fly ash from coal, fertilizers that rewrite nitrogen cycles, and a razor-thin horizon where man-made radionuclides born in nuclear tests rained out across the planet. That mid-20th century fallout line is as sharp as a page break. It's one reason scientists chose a tiny, still Canadian lake with annual layers like tree rings to represent our current planetary impact. Year by year, you can read the arrival of the modern world. Whether or not the Anthropocene earns a permanent place on the official timescale, its geologic signal is undeniable. And the very existence of that signal teaches us what to look for if we were not the first. So we begin here, in the gap between what we expect and what the Earth preserves. We expect skyscrapers. The Earth keeps chemistry. We want a lost library. The Earth gives us a line of altered carbon and a dusting of artificial elements. If an earlier industry ever bloomed and burned out, its story would not be told in grand ruins, but in the quiet language of rock. Here's the paradox that will carry us forward. Absence of ruins is not absence of civilization. The question is whether deep time leaves any signature that is both global and weird enough to rule out volcanoes, meteor impacts, or natural climate swings. If the answer is yes, then we can search for it. If the answer is no, then humanity's own layer, our plastics, our soot, our brief radioactive breath may be the only whisper that civilizations ever get. So, could there have been another? And if so, where in the planet's stony memory would we find their shadow? The paradox starts with a simple, unsettling thought experiment. If a planet-wide, tool-using, energy-hungry civilization rose and fell long before us, would we mistake its remains for nature? We're used to history leaving statues and scripts. Geology, however, speaks in chemistry and pattern. So the question isn't, where are their cities? But, is there anything in Earth's deep archive that looks like deliberate industry rather than volcanoes, wildfires, or asteroid strikes? That framing has a name, the Silurian Hypothesis. It doesn't claim there was a pre-human civilization. It asks what evidence would be necessary if there had been one, and just as important, how we'd avoid fooling ourselves. Imagine science setting up an evidence trap with two rules. The signal must be one, global, because an industrial species at scale touches the whole planet, and two, weird, meaning it can't be easily explained by normal geology or biology. Global and weird is a high bar, but it gives us something to look for besides fables. Begin with carbon, the bloodstream of life, and the backbone of fuels. Burning fossil carbon leaves fingerprints. The ratio of lighter to heavier carbon isotopes shifts in a particular direction when ancient organic matter is rapidly injected into the atmosphere. In our time, that isotopic nudge, combined with a sudden spike in greenhouse gases and warming, forms a distinctive bundle. If we found a similar bundle in, say, a 20 million-year-old layer, would that prove industry? Not yet. Nature has pulled off rapid warming events before volcanic pulses, methane burps from the seafloor, even massive peat fires. So the hypothesis says, don't rely on a single clue. Build a suite. Next, the technofossils, the artifacts that geology can actually keep. Plastics fragment and degrade, but some polymer residues bond to sediments. Aluminum and copper alloys corrode, yet leave mineralogical hints. Concrete can recrystallize into odd cements. Even biology changes. Domesticated animals proliferate into the billions. If a layer held a sudden, worldwide bloom of uniform bone morphologies, think the same engineered body plan appearing on every continent that would be. Our own era's broiler chicken is a perfect example. A global lineage, accelerated growth, consistent anatomy. It's the sort of quirk a future paleontologist might flag as non-natural. Then there's fallout. Mid-20th century nuclear tests dusted the planet with radionuclides that don't occur in significant amounts by themselves in nature, and that decay on timescales long enough to mark a razor-thin line. Even if civilizational ruins vanished, a planet-wide pulse of artificial isotopes would remain as a timestamp, a sudden, synchronized whisper. Someone was here. But the Earth is a trickster. Volcanoes can spread heavy metals. Lightning and fires can make odd glass. Meteors can spike iridium. How do we keep from seeing faces in the clouds? The Silurian Hypothesis says to look for coincidence in complexity. Multiple independent anomalies, stacking in the same narrow window. An isotopic lurch, a sedimentary shift toward microplastics-like residues, a bloom of combustion particles, a spike of synthetic radionuclides or unusual alloy oxides, a biosphere reshuffling that favors opportunistic species, and a handful of hyperabundant morphs. Any one of these can be natural. All of them together, globally synchronized, that's where nature runs out of easy explanations. There's also the problem of preservation bias. Oceans eat their own floor, mountains crumble, river plains are rewritten with every change in course. The most continuous records form in quiet, anoxic places. Deep basins, still lakes, certain marine shelves, where year after year, particle-thin layers stack without being stirred. If an earlier civilization was brief, if its industrial phase lasted centuries or even a few millennia, its entire pulse might compress into a layer thinner than your fingernail. Finding it would demand not a treasure hunter's map, but a planet-scale audit of mud. And what if we did find something compelling? Suppose a research corps pulls up a layer showing an abrupt carbon isotope excursion, pervasive soot, curious polymer-like residues, and scattered anomalies in metals, all tightly bunched and global. We would still face the null hypothesis. Can a natural scenario explain this? A flood basalt event? A methane clathrate release? A lightning-sparked wildfire age? The burden wouldn't be to prove industry in the abstract, but to demonstrate that a natural stack like this would be vanishingly unlikely. In other words, the Silurian hypothesis doesn't lower our standards, it raises them. It asks us to be ruthless skeptics, even of our most thrilling evidence. That's the paradox in focus. The more scientifically careful we are, the harder it becomes to declare someone was here. Yet that very caution is what makes the search meaningful. It keeps us from telling ourselves comfortable myths or from missing a genuine, humbling discovery because it didn't look like a lost temple. So we approach the rest of this investigation with two guiding lights. First, bundled signals beat single anomalies. Second, comparative cases, our own modern layer, known natural hypothermals, impact horizons. Volcanic provinces are not distractions. They are controls. They teach us what industry would have to defeat to stand out in stone. If deep time hides civilizations, we won't uncover them by dreaming about Atlantis. We'll do it by reading the planet's memory like a forensic ledger. Line items, cross-checks, and signatures that add up to intention. Before we go hunting for ghosts in ancient rock, we have one priceless advantage. A living control sample, us. If a future civilization drilled into our century, what unmistakable bundle would tell them an industrial species had bloomed here? Start with a lake barely a kilometer across, ringed by cedars in Ontario. Crawford Lake is unusually deep for its size. Water below a sharp density boundary doesn't mix with the surface. So every year, a paper-thin layer settles to the bottom like a page in a diary. Core those varves, and you can literally count time, year by year, through the 20th century. What you see is not myth or metaphor, but chemistry and ash. A sudden arrival of bomb-spawned radionuclides plutonium-239, cesium-137, followed by a pulse of industrial particles and nutrients that reshape the lake's biology. It's a crisp, planetary page break that scientists nominated as a golden spike for our age. Even though the Anthropocene was not ratified as a formal epoch in 2024, the signal itself is unambiguous. Then the plastics arrive, not just bottles and bags, but microscopic shards and fibers drifting into rivers, estuaries, continental shelves getting pressed into muds that will one day be stone. Researchers are already building chronologies of microplastics in dated sediment cores. The polymers evolve in lockstep with industry, a timeline written in chemistry. Plastics are so pervasive that geologists now debate them as technofossils artifacts that future rocks will remember. Our biology broadcasts the story too. Consider the broiler chicken, a deliberately engineered body plan, produced by the tens of billions, with bone shapes and growth rates unlike any wild ancestor. Their remains are globally distributed in landfills and sediments, an artificial species whose fossils future paleontologists could mistake for a sudden, uniform radiation across every continent. If you wanted a single skeleton to stand in for the human rearrangement of life, this would be it. Add metals and minerals, spikes of fly ash from coal combustion, unusual distributions of lead, copper, and chromium, concretes and cements that recrystallize into odd lithologies. Stir in nitrogen and carbon isotope, shifts from fossil fuel burning and industrial agriculture. Stack all of that with the radionuclide timestamp of mid-century nuclear tests, and you get a bundle multiple independent anomalies, globally synchronized, tightly packed into a layer thinner than a finger. That bundle is the yardstick by which we can judge any deep-time mystery. And yet here's the twist that raises the stakes. Science just reminded us that signals and systems are not the same as names. In March 2024, the International Union of Geological Sciences decided not to formalize the Anthropocene as a new epoch. The Holocene remains official, but the vote did not erase the data. It sharpened the question. Our imprint is geologically real even if the timescale stays conservative. So when we look backward into ancient stone, we aren't chasing legend, we're asking whether a comparable bundle ever appeared before, and whether nature alone could have produced it. This is why our era matters to the hunt. Crawford Lake's page-by-page narrative shows the shape of an industrial pulse. Abrupt, global, and multiplex radiation, plastics, ashes, isotopes, bones. Plastics tell us that durable synthetics can ride the sediment conveyor into the far future. Chickens tell us that domestication leaves a traceable anatomical signature. Radionuclides tell us that even brief technologies can etch a razor-thin line into planetary memory. Put together, they teach us what to look for and how hard we have to work to rule out volcanic paroxysms, methane spills, and other natural tricksters. So the stakes aren't just academic. If deep time once held another industry, its echo would have to fight through the same noise ours is making: erosion, subduction, the chaos of natural climate swings. Our bundle shows it's possible to stand out anyway, which means this investigation isn't a fairy tale. It's a falsifiable search, armed with a living template. We can now turn the lens to forensics. What exactly would a prior civilization leave behind in rock, and where would those clues most likely survive? Imagine trying to reconstruct a novel from a handful of letters baked into clay. That's geology. The planet is always writing, but it also loves to edit ruthlessly. Start with the biggest eraser: plate tectonics. Oceanic crust is a conveyor belt that dives back into the mantle on a cycle of tens to hundreds of millions of years. That means vast swaths of seafloor where a coastal, trade-loving civilization would likely concentrate are periodically swallowed. Even on land, mountains rise and weather down, basins fill and are uplifted. Rivers rearrange the map every few thousand years. The archive we inherit is not a shelf of neatly bound volumes, but a patchwork scrapbook with missing chapters and coffee stains. Where, then, does the planet keep the neat pages? In low-energy, anoxic basins, places with sluggish water, little oxygen, and minimal burrowing by animals. There, fine particles settle like dust on a sleeping table, layer upon layer, preserving annual laminations the way tree rings do. Varved lakes are the crown jewels. Certain restricted marine basins and continental shelves can also behave like slow, patient scribes. In these places, thin time survives. A few millimeters of mud might hold decades, sometimes centuries, of history without being smeared by waves or worms. But these friendly archives come with costs. Lakes are local. A single watershed can dominate the chemistry, risking false positives from regional industry or volcanism. Marine basins are dynamic. Currents shift. Oxygen leaks in. Storms stir up layers. Even an excellent site can flip states. Today's calm, anoxic bowl may become tomorrow's well-oxygenated trough after a climatic or tectonic nudge. And the very anoxia that preserves chemistry also encourages diagenesis post-burial reactions that can alter signals. Iron locks onto phosphorus. Sulfide minerals grow. Organic molecules crack and rearrange. The writing remains, but its ink can blur. There's also sampling bias. We core where we can get permits, where politics allow, where icebreakers and research ships can reach, where sediments are thick enough to justify drilling budgets. That practical reality skews our picture of the past toward coastlines of wealthy countries, navigable seas, and charismatic lakes. If an ancient industrial pulse peaked in basins we haven't yet sampled or in strata, now buried deep beneath cities and farmland, we may simply be looking in the wrong rooms. Even when we find a promising archive, resolution becomes a gatekeeper. If a civilization's industrial sprint lasted 300 years and our core compresses those centuries into a single centimeter, we need sampling and dating fine enough to resolve the signal. That means careful subsampling, millimeter slices, multiple independent clocks, radiocarbon, VARV counts, tephra ties, paleomagnetic flips, and global correlation, linking the same thin horizon across continents. Without that correlation, a weird layer is just weird. Finally, consider burial depth. Many of the best continuous archives sit in basins that continue to accumulate sediment, burying their most interesting chapters hundreds of meters down. Accessing them requires specialized rigs, budgets, and years of planning. Meanwhile, the sections we can hike to are often eroded, faulted, or oxidized, beautiful to the eye, treacherous to the chemist. Rock archive bias is not just about what the Earth preserves, it's about what we can reach without disturbing the very signals we hope to read. So the search strategy is a compromise. We prioritize quiet basins with tight layering, triangulate with rapidly accumulating shelves that give us thickness, and cross-check with uplifted ancient strata that offer a glimpse into deep time. We accept that the archive is unfair, and we design our questions to survive that unfairness. Don't rely on a single site. Demand a chorus across many. Suppose you pull a core that shows a sharp warming, a plunge in carbon isotopes, black soot, and stressed marine life. Congratulations, you've found something. But what? Nature is a master of false positives. Consider just a few impersonators. Large igneous provinces, Titanic. Volcanic outpourings can belch carbon dioxide and aerosols for millennia, acidify oceans, spread heavy metals, and dust the world with glassy particles. Their fingerprints include basaltic provinces, sulfur isotope quirks, and extended multi-phase signals, not a crisp, century-scale spike, but a smeared saga. Methane releases. Destabilized clathrates can dump light carbon into the ocean atmosphere system, driving negative delta to the power of 13C excursions and warming. They leave widespread carbonate dissolution and specific biomarker shifts, but usually lack any synthetic companions: plastics, alloy-derived oxides, non-natural radionuclides. Wildfire ages. Continental-scale burn periods can blanket sediments with charcoal and soot, redden soils, and tweak nitrogen cycles. But wildfire products differ morphologically and chemically from high-temperature industrial combustion microspheres. They also map to climate patterns rather than supply chains. Impacts. Asteroid strikes can spike iridium, shatter quartz, ignite global fires, and trigger brief warming pulses. They tend to leave unmistakable ejecta layers and shocked minerals dramatic, but wrong shape for multi-century industry. Anoxia waves. Ocean circulation reorganizations can create black shales rich in organic carbon, metals, and biomarkers of stressed ecosystems. These often unfold over thousands of years and are tied to orbital pacing or tectonic bottlenecks. The Silurian approach is to require coincidence in complexity. Multiple independent anomalies, tightly synchronized, that together strain natural explanations. A strong technosignature candidate would bundle 1. A rapid negative delta to the power of 13C excursion. 2. A contemporaneous nitrogen cycle disturbance. 3. Combustion microspheres with industrial morphologies. 4. Technofossil residues, polymeric fragments, odd cements, engineered glass. 5. Radionuclide anomalies or other unmistakably artificial isotopes or their ancient analogues. And 6. A biosphere reshuffle featuring a sudden bloom of uniform domesticate-like morphologies. Each of these has natural doppelgangers. All together, arriving within decades to centuries across many basins, is where nature runs out of stage tricks. Even then, we must battle taphonomy, how things decay and fossilize, and diagenesis, how they change after burial. Plastics cross-link or carbonize. Metals oxidize into minerals we might mistake for weathering products. Concrete recrystallizes. Radionuclides migrate a bit with pore waters. That's why we lean on morphology, plus chemistry, plus context. A single fiber is ambiguous. A population of fibers with uniform polymer chemistry, thickness distributions, and co-location with combustion spheres and fallout-like isotopes is a narrative. Dating is the other arena where confusion breeds. Marine cores may have reservoir effects that offset radiocarbon ages. Lakes can suffer from old carbon contamination. The cure is redundancy. VARV counts, tephra layers with known eruption ages, paleomagnetic reversals, and, where possible, annual or decadal markers. A convincing technosignature candidate would be one we can pin to a narrow time window in multiple archives using multiple clocks, all agreeing within error bars. Finally, we guard against our own pattern hunger. Humans are gifted at seeing faces in clouds and civilizations in coal seams. The antidote is pre-registered criteria. Define in advance what bundle of signals counts as industrial. Apply those criteria blindly to many intervals and publish the misses as well as the hits. Only then do we earn the right to call a weird layer more than a coincidence. Civilizations, by their nature, are brief. Even if one lasted 10,000 years, a staggering run. By human standards, that's a single pixel on Earth's 4.5 billion year canvas. Geology can blur pixels. Picture 3 clocks running at once. Deposition rate. In slow settings, the deep open ocean a millennium might be a few millimeters of ooze. In fast settings, deltas, floodplains, storms, and floods lay down thick, chaotic beds that mix signals. Our hypothetical industrial pulse must be caught where time is neither too thin to sample nor too thick to smear. Surface churn. The top few meters of the Earth are a blender. Roots pry, insects burrow, rivers meander, frost heaves, dunes migrate. An industrial layer on land risks being reworked into younger sediments, turning a clean line into a mottled haze. Even in lakes, burrowing organisms can stir the top layers unless anoxia keeps them at bay. Long burial, given enough time and pressure, sediments lithify, turn to rock, then deform, heat, and chemically alter. The very processes that make rock readable also threaten to erase the fine details that distinguish industrial from natural. A crisp radionuclide horizon might diffuse. Polymer residues might collapse into indistinct carbon. Concrete might become an oddly composed limestone. Erosion is the fourth. Silent clock always ticking, always subtracting pages. River terraces are planed off. Coastlines retreat. Glaciers bulldoze. Landscapes clean. Deserts scour bedrock. Most of whatever happens on the surface does not become part of the permanent record. That's not pessimism, it's design. Earth prefers renewal over memory. So how do you outwit time? You go wide and deep. Wide, by sampling many basins across climates and continents, so that local erosion or reworking at one site doesn't kill the signal everywhere. Deep, by coring into thick stacks where the industrial horizon is quickly buried below the zone of biological mixing and storm disturbance. You also aim for event trap settings that capture abrupt inputs. Landslide-dammed lakes, fjords with sills that limit circulation, foreland basins that gulp sediment after mountain building, and karstic sink lakes that archive year-by-year pages. You also accept that our best bets for detecting an ancient industry may not be today's scenic outcrops but tomorrow's drill cores. The quiet, cylindrical biographies pulled from beneath deserts, deltas, and continental shelves. The irony is sharp. If we're not the first, their clearest signature might hide in places we rarely look, or can only reach with technology born of our own industry. Even then, humility is warranted. We may never get a smoking gun. We may only get likelihoods bundles that make natural explanations awkward but not impossible. But probability is how science moves across large uncertainties. If, in 10 different basins, we map the same thin horizon with the same weird chorus of signals, carbon and nitrogen jolts, combustion spheres, technofossil residues, alloy-derived oxides, and some analog of artificial radionuclides arriving within centuries, then eroded, then gone. That pattern, repeating despite erosion's cruelty, would itself be an argument. Time hides, but it also rhymes. If we listen in enough places, the planet's memory can still sing. If you want to catch a ghost, start with your reflection. Our era is the one moment in Earth's history where we can test, in real time, what an industrial civilization looks like in stone. That makes us both subject and instrument, an uncomfortable but powerful position. So let's walk through the places where the planet is already archiving our story, and treat them as benchmarks for any deep time mystery. Begin again at the water's quiet edge. Involved lakes: Crawford Lake in Ontario, Lake Sihailongwan in China, Searsville in California. Fine seasonal layers settle like dust on a table no one touches. Through the 20th century, those paper-thin laminations change character. A chemist's thumbprint appears. Plutonium, cesium, and the bomb pine of sea pulse ink, a razor horizon that brackets the early 1950 seconds to early 60 seconds. Black specks of combustion spheres multiply. A drift of fly ash and soot grows. Ratios of carbon and nitrogen shift as fossil carbon floods the air and fertilizer floods watersheds. Algal blooms wax and wane. You can read this history almost year by year, a thriller if you like geology with your drama. What makes these lakes so valuable isn't just clarity, it's coherence. In core after core, on separate continents, the same bundle appears almost in unison. The fallout line, the spike in industrial particles, the isotopic lurch, biological reshuffles. We rarely get fossils, buildings, or artifacts in these muds. We get systems reacting, physics and chemistry adjusting to a sudden, planet-wide experiment. That's the control pattern we carry forward. Brief, global, multiplex. Now, shift to the continental shelves, the broad, shallow seas, where rivers pour their silt and cities cluster. Here, sedimentation is faster than in the open ocean, and time thickens into centimeters per century. That extra thickness lets more of our debris survive. Microplastics tumble in with clays. Synthetic fibers snag on organic flocks. Urban conglomerates from coastal construction and storm-dismantled infrastructure add strange gravels to deltas and estuaries. When hurricanes and typhoons roar through, they tear bits of the built world into the record. Sand infused with glass beads, crushed concrete grains, rust halos where rebar once lay. None of those grains says skyscraper out loud. Together they say coastlines run by industry. From shelves we leap offshore, chasing the faintest but most widespread voice: the open ocean. Here, sediment falls so slowly that a millennium might barely cover your fingernail. You'd think our presence would vanish into that thinness, but chemistry magnifies whispers. The ocean absorbs much of our emitted CO2. Carbonate shells grow under slightly more acidic conditions. Deep currents redistribute the signal. In the North Atlantic's deep muds and in Southern Ocean oozes, you can trace the Suez effect, the dilution of Banfortsi by fossil carbon, and subtle shifts in carbonate's isotopic makeup. Microplastics get everywhere, even into abyssal clays. And although waves and time break them down, polymer residues persist enough to be counted and compositionally mapped. If a core from the abyss can catch us, then an ancient industry's footprint, if it reached into oceans, might be faint but not invisible. Head poleward. Ice is not rock, but it is a moral teacher in stratigraphy. It stacks years in order, protects fragile clues, and hands them back with timestamps. The mid-century bomb pulse in 940 and tritium, Kokub, runs through polar and alpine ice like a neon thread. Sulfates and nitrates spike with industrial smog. Lead rises with leaded gasoline, then falls after policy changed. Black carbon tells a story of coal, diesel, and wildfire. These are not technofossils in the classical, rocky sense, but they are calibration marks for the rest of the planet's archives. The lake says, something happened. The ice says, here's when. Now zoom into soils and landfills, the unglamorous places where civilizations exhale, Soils absorb our fertilizers, shifting delta to the power of 15N. They host microplastics blown from farms and city edges. They archive a rain of metals from industry and traffic. Landfills concentrate the strange. Metals in improbable combinations, electronics ground into glittering dust, organics mummified in anoxic pockets. Bury those hills under flood sediments or sea level rise, give them a few thousand years, and they become composite rock bodies with geochemistries that nature simply doesn't assemble on its own. They're messy, local, and utterly diagnostic. Biology chimes in as chorus and metronome. The broiler chicken, a standardized global body plan, dominates bone assemblages by sheer abundance. House mice, Norway rats, pigeons, and urban-adapted foxes expand their ranges, riding our trade routes and cities. In the oceans, jellyfish blooms pulse where nutrient runoff and warming destabilize ecosystems. Fishing pressure rearranges marine food webs, leaving telltale signatures in otolith chemistry and population structures. These are not just anecdotes. They're ecological fingerprints that translate into sedimentary signals, bones, scales, biomarkers aligned with the industrial bundle. And there is one more control case we sometimes overlook: policy. The planet's stratigraphy records our decisions. The 1,963 partial test ban clipped the radionuclide tap almost overnight. The phase-out of leaded gasoline bent the lead curve back downward in ice and lake sediments. Clean air laws changed sulfate and nitrate deposition trends. CFC bans left scars in atmospheric chemistry that will fade only over decades. If you're hunting an ancient industry, ask whether the layer speaks of on divided by off switches, abrupt global turns that make no sense as volcanism or orbital cycles. Policy leaves stratigraphy that nature does not. Why does this grand tour matter? Because it reveals a shape that is hard to imitate. Global synchronization within years to decades, not millennia. Multi-proxy agreement. Isotopes plus particles plus technofossils plus biology. Directional reversals tied to behavior. Policy, not to tectonics or precession. Geographic logic that follows coasts, rivers, and trade, not climate belts alone. A thin, coherent horizon in quiet basins, and a thicker, jumbled one in fast-depositing shelves and deltas, both carrying the same chemical DNA. Hold that template next to any deep-time candidate, and you can start asking disciplined questions. Is the carbon isotope excursion fast enough? Do we see coeval nitrogen cycle upheaval? Are there combustion spheres with industrial morphologies instead of wildfire charcoal alone? Synthetic residues or odd cements? Do metals and rare earth elements appear in ratios that whisper refining and e-waste rather than weathering? Does the signal show an abrupt cutoff that looks like behavior rather than lava running out? Our control case also sets healthy expectations about imperfection. Even with satellites, mass spectrometers, and global networks, our own layer is uneven. Cities concentrate debris, deserts filter signals through dust, monsoons smear time with floods. Yet, despite patchiness, the bundle holds. That is liberating for the deep time search. You do not need a perfect record everywhere. You need a conciliant one across enough places to make coincidence implausible. There's a final, humbling note here. When we treat our century as data, when we boil it down to ratios, spheres, and spikes, we briefly step outside ourselves. We see humanity not as a story we tell about progress or crisis, but as a stratigraphic event in a 4 billion year ledger. If another species ever lit the world and then went dark, the clearest thing we might inherit from them is exactly this kind of ensemble. Chemistry that moved too quickly, materials that don't quite fit, bones that multiplied everywhere at once. Our reflection becomes their outline. Armed with that control, we're ready for the harder question. Are there ancient lookalikes moments in deep time that flirt with our template, that tempt us to say, maybe, and force us to test natural until it breaks? If you want to know what a counterfeit looks like, study the best fakes in the museum. Deep time has a few. The most famous is the Paleocene-Eocene thermal maximum. The PETM, about 56 million years ago. In geological terms, it's a siren. Carbon isotopes plunge, temperatures jump, oceans acidify, and ecosystems scramble. If you squint, it's our century stretched and blurred, but look closely, and the differences matter. The PETM's onset, while geologically abrupt, likely unfolded over thousands of years. Ours compresses into mere centuries. There's no whisper of synthetic residues, no global suite of long-lived artificial radionuclides, no standardized bone flood of domesticated morphologies. The PETM teaches humility. Nature can stage a drama that echoes our signature, but it also sets a bar. Speed, synchronicity, and multi-proxy oddity are the hurdles any deep-time industry must clear. Zoom out to a broader family. The Eocene hypothermals, smaller siblings of the PETM. They're like echoes in a canyon, repeating bursts of warming, carbon swings, and ecological stress. Each shows us how orbital pacing and carbon cycling can conspire to mimic pieces of our bundle without ever assembling the whole. If you find a thin horizon in some ancient basin with a PETM-like carbon jolt, you've found a candidate, not a civilization. The test is whether that layer drags along independent weirdness, technofossil-like residues, combustion microspheres with industrial morphologies, alloy-derived oxides, or an analog to bomb-era radionuclides. So far, the hypothermals don't. Consider the spectacular villains of geology. Large igneous provinces, LIPs. When a planet opens a mantle tap, it can flood continents with basalt for hundreds of thousands of years. The Siberian traps around 252 million years ago correlate with the end Permian mass extinction, the worst die-off we know. The Deccan traps accompany the end Cretaceous turmoil. Lips push CO2, sulfur, metals. They blacken skies, sour oceans, and leave behind kilometers-thick lava stacks a physical calling card industry could never hide. Their time signature sprawls. Pulses within the outpourings can be brisk, but the envelope is long. If your mysterious layer coincides with a basaltic province the size of a small country, odds are you're reading magma, not machines. Then there are impact horizons. The end Cretaceous boundary is a masterclass in planetary punctuation. A. Global dust of iridium, shocked quartz, microtectites, wildfire residues. A sudden reset in fossils. It's brutally synchronous, yes, but its ingredients and shapes are textbook natural. The iridium spike, the spherules, the tsunami beds, the crater itself. If you ever found a thin layer as globally crisp as the KPG boundary without impact proxies yet with industrial oddities, you'd have the world's attention. Until then, impacts remain the wrong recipe for industry, even if they share the right tempo. What about enigmatic black shales and anoxic crises? Oceanic anoxic events, OAEs, sprinkled through the Mesozoic. These intervals record widespread oxygen loss, high organic carbon burial, trace metal enrichments, and stressed marine ecosystems. They can cluster, recur, and persist for hundreds of thousands of years. Again, That's the wrong shape for a civilization's abrupt rise and fall. And while OAEs may carry soot and elevated metals, their geochemical fingerprints align with tectonics, volcanism, and biogeochemical feedbacks, not synthetic residues or policy like on divided by off switches. There are also regional curios, oddities that, in isolation, can tempt a storyteller. A coal seam peppered with spherical carbon particles, a lacustrine shale with spikes of certain metals, a deltaic sand bed stuffed with angular man-made looking grains. Natural processes can make all of these. Lightning and high-temperature wildfires form glassy spheres. Floods bulldoze city-like rubble out of mountains. Hydrothermal veins produce alloy-like assemblages that aren't alloys at all. The antidote to temptation is context. Do nearby basins sing the same note at the same time? Do multiple independent proxies agree? Are there global tie points? Without those, a curiosity is just that. If deep time holds a real look-alike, it will probably sit where our control case says to look, in quiet, well-dated basins that preserve thin time cleanly. So what would elevate a PETM-style mystery to a true technosignature candidate? Tempo, a negative carbon isotope excursion collapsing in decades to centuries, not millennia. Synchrony, near simultaneous onset, across continents and oceans, not staggered by ocean circulation lags alone. Companions, industrial morphology, combustion microspheres, polymer-like residues, odd cements, or urban conglomerate textures, metal ratios consistent with refining, not weathering, and any analog to artificial radionuclides. Behavioral shapes, abrupt cutoffs or reversals that suggest decision points, an on divided by off pattern hard to draw with volcanoes or orbital cycles. Biotic strangeness, a sudden global bloom of standardized morphologies, anatomically uniform bones or shells that appear everywhere at once and then decline. Some researchers point to brief, intense events, mystery-warming spikes inside longer crises, or narrow soot layers nested in broader trends as places to look harder. Those are exactly the edges where industry could hide inside noise, a thin chapter within a thick book. But until the multi-proxy bundle shows up, the conservative read stays natural. There's also an uncomfortable possibility. If a prior civilization never split atoms, never mass-produced persistent polymers, and kept its industry largely local, its layer might be almost indistinguishable from regional volcanism and land use changes. The planet might only remember them as a slight carbon burp, a few odd minerals, and a short-lived reshuffling of species subglobal and ambiguous. In that scenario, absence of proof isn't proof of absence. It's a reminder that detectability depends on choices. The more a civilization globalizes extraction, energy, and waste, the more legible it becomes to the future, which circles back to why the lookalikes matter. They aren't disappointment, they're calibration. Every natural imposter we can explain tightens the net around what would count as truly weird. Each hyperthermal, each LIP, each OAE is a rehearsal for the day we pull a core and the data refuse to play by nature's rules. If that day never comes, we at least gain a richer understanding of the planet's ability to change itself fast, hard, and without anyone's help. If somewhere, in a varved lake uplifted from an ancient basin, a millimeter-thin layer reveals a century-scale carbon plunge, an echo in nitrogen, a bloom of industrial-shaped microspheres, polymeric ghosts, alloy-borne oxides, and a brief, global reshuffling of bones, then the conversation changes. Not to certainty, but to seriousness. we would be compelled to test, to replicate, to disprove and fail, and only then to whisper, maybe we weren't the first. If Earth is a restless librarian, the Moon is a hoarder. No rain, no rivers, no plate tectonics, just vacuum, radiation, and a slow drizzle of micrometeorites. That makes the lunar surface a kind of control shelf for civilization, a place where artifacts can outlast continents. If a prior industry ever climbed off-world even modestly, the Moon is the most likely place a trace would endure. Preservation there is strange but generous. Metals corrode on Earth. On the Moon, they embrittle under ultraviolet light and thermal cycling, then get peppered by micrometeorites that sand everything into a fine, glassy dust. That's destructive, but it's slow millimeters per million years in many terrains. Buried a few centimeters, an object can nap for geologic time. In lava tubes and permanently shadowed craters, temperatures are stable and volatiles sit undisturbed. A cache of hardware in those cold vaults could sleep for eons with only minor alteration. So, what would we look for? Geometry against geology. Nature does curves, cones, fractures, dunes. Industry does grids, parallel lines, right angles, and repetition at human scales. A field of evenly spaced pylons, a rectilinear foundation pad, or the footprint of a landing pad, baked into regolith would contrast sharply with the Moon's chaotic textures. Material oddities. Lunar rocks are rich in silicates and oxides. They do not contain wrought alloys, soldiers of fasteners, polymer binders, or multi-layer composites. Even if those materials degrade, they leave residue chemistries, alloyed titanium with vanadium patterns, exotic steels, epoxy-derived organics that don't match lunar baselines. Micrometeorite glass is one thing. Tempered window glass or fiber optics is another. Mining scars. Strip a patch of regolith for metals or oxygen, and you alter albedo and texture in ways that don't look like impact gardening. Trenches with uniform widths, spoil piles with consistent angles, or tailings arranged upslope from pits would read like a factory diagram. On Earth, rivers erase such scars. On the Moon, they freeze in place. Thermal and spectral fingerprints. The Moon's day-night swings make man-made debris radiate heat differently than rock. Even if objects are buried, disturbed soils retain heat in distinctive ways. Spectrally, paints, polymers, and glass coatings have non-lunar absorption features weak after ages of space weathering, but still statistically weird in aggregate. Contextual nonsense. A smooth boulder perched on a powder slope can be natural. A smooth boulder with repeat drill holes every 10 centimeters is not. Likewise, a patch of melted regolith, trinitite-like glass, next to symmetrical blast, scours hints at directed energy rather than lightning or meteoroids. Skeptics will point out space weathering, solar wind implantation, micrometeorite vitrification, charged dust transport. True, these blur edges and dull spectra, but they blur everything slowly and roughly evenly. The antidote is pattern and redundancy. Multiple sites with the same unnatural geometry, residues repeating the same alloy ratios, scars with matching widths that track latitude and not local slope. Like on Earth, we don't bet on a single anomaly, we bet on a bundle that forces a conclusion. If the Moon is the vault, lava tubes are the safety deposit boxes. Their roofs shield from micrometeorites and radiation. Their floors are thermally calm. A prior civilization that understood preservation even instinctively would stash high-value hardware there. Navigation beacons, power systems, archives. spare parts. On Earth, caves keep Paleolithic art. On the Moon, they could keep Paleotechnic art machine traces that still carry manufacturer logic. What about Mars? It adds atmosphere, weather, and chemistry, good for erosion, bad for preservation, but also gifts us sedimentary rocks and ice. The polar layer deposits on Mars stack climate pages like a drum roll. If someone seeded the planet with probes or small stations, ejector-protected fragments could persist for tens of millions of years. Martian caves, too, might hide equipment from wind and ultraviolet. But because Mars weathers faster than the Moon, it's a weaker long-term shelf. And asteroids, if a civilization mined near-Earth asteroids, it might have left regolith tailings, anchoring scars, or unusual spin state changes from momentum exchange, subtle clues that demand precise surveys and before divided by after baselines. In the main belt, debris from failed hardware could orbit for ages. In practice, the population is noisy and collisions are constant, making the signal faint unless activity was massive. There's a meta-argument here. If you can reach space, you often must. Orbital relays, weather monitoring, global positioning. These are natural attractors for industry. Once there, you quickly learn that the Moon is a perfect workshop. Vacuum metallurgy, cold storage, abundant regolith for shielding. The leap from industrial to cislunar infrastructure is short by civilizational standards. That's why the absence of obvious lunar technosignatures would not disprove prior industry on Earth, but their presence would be the cleanest proof. How, practically, would the search proceed? High-resolution orbital imaging to flag geometries, multispectral and thermal surveys to detect material anomalies, radar and gravimetry to peek into lava tubes, ground truth with small rovers targeted at the strangest candidates, and crucially statistical tests that compare candidate sites to large control sets of natural features. If a dozen craters show rim-top arrays with consistent spacing, aligned to true east across latitudes, geology runs out of excuses. Finally, philosophy. We often dream of ancient cities under jungles because we think in ruins. Off-world, we have to think in systems. A grid of footpads on a moonscape is a sentence. A network of landing sites, cable trenches, and buried tanks is a paragraph. If anyone wrote on the Moon before us, their pen strokes would still lie in the dust, patient, indifferent, and legible to anyone curious enough to read. Before we imagine strangers lighting Earth long ago, we should be honest about ourselves. How long did it take us to get here? What did the climb look like? And where did it almost fail? The answers turn our speculation into measure. Start far upstream. At 3.3 million years ago, on a scrubby lakeshore now called Lomekwi in Kenya, hands chipped stone into edges. That act, the decision to strike one rock with another to make a third thing with a purpose, was a hinge in evolution. Yet from that hinge to industry is not a straight hallway. It's a staircase with landings and dead ends. Oldowan flakes become Acheulean hand axes. Fire is coaxed and then mastered. Seasonality and memory knit into strategies. Language thickens. Brains don't just grow, they rewire. By 300,000 years ago, Homo sapiens stands in the mirror in Africa with a face we'd recognize. But recognition isn't destiny. For most of our tenure, we live in small, mobile bands. The world is cold more often than warm. Ice lords over temperate latitudes. Numbers matter. Here, hunter-gatherers often stabilize at densities where a valley feeds a people, not a city. Technological takeoff requires surplus. and surplus requires settlement. And settlement binds us to cycles of sowing, harvest, storage, and taxation. The first quiet algorithms of states. That binding begins late. Agriculture arrives independently in a handful of places between 12,000 and 4,000 years ago. The Fertile Crescent, the Yangtze and Yellow River basins, Mesoamerica, the Andes, and the Sahel. It's not inevitable. It's an invention repeated by need and opportunity. With farms come villages, with villages defenses, with defenses hierarchies, with hierarchies writing first for grain and debt, then for kings and gods, and eventually for laws, poems, and bored scribes. Bronze follows copper. Tin becomes a strategic mineral. Long-distance trade knits the fringes into a fabric. If we plot a human paceline, the Holocene, the last to 11,700 years, is the last lap where our speed spikes. Even then, the leap to industry, to machines that multiply muscle with fossil heat, waits until yesterday. Water wheels hum in Roman and Chinese mills. Windmills come later. But for a very long time, energy comes from wood, hay, and hunger from forests, fields, and bodies. Metal is expensive. Steel is rare. Glass is a craft. Roads are stone and sweat. Empires rise and glitter and fail without ever multiplying their energy base by orders of magnitude. The steam engines trick boiling water with coal to harvest pressure as power lands in the 18th century because the scaffolding beneath it is finally ready. Metallurgy steady enough to make cylinders, finance nimble enough to fund risk, science formal enough to iterate, markets hungry enough to consume. When we ask, could there have been a human industrial civilization earlier that we somehow missed? The timeline answers with constraints. Constraint 1. Energy density. Pre-industrial societies lack dense, portable energy sources beyond animal fats and charcoal. Coal seams sit in the dark until geology, metallurgy, and capital conspire to tap them. An earlier sapiens industry would need not just ingenuity but stacked preconditions: accessible coal or oil, smeltable ores, large-scale water management, and social structures to coordinate labor across generations. That stack appears late in our story. Constraint 2. Population and networks. Industry is not a lone genius. It is a network effect, knowledge shared, improved, protected, stolen. Supply chains that gather ore here, coal there, grain over there, mines everywhere. For most of human time, population is small single-digit millions, then tens of millions scattered thin over continents. The carrying capacity of hunter-gatherer landscapes keeps numbers low. Even early farmers fight ceilings. Harvest variability, disease, salinized soils, elites siphoning surplus. Without cities that accumulate people and problems, you don't get the pressure cookers that forge engineering. Constraint 3. Records and residues. Humans are excellent litterers of time. Stone tools blunt slowly and scatter widely. Hearths leave reddened earth and charcoal. Bones bear cut marks. Ochre-stained shells whisper of art. When we settle, we leave post holes, wall trenches, midden heaps rich in fish bones and broken pots. By 10,000 years ago, the map blooms with traces. Göbekli Tepe in Anatolia, monumental stone circles raised by hunter-gatherers, Jericho with its tower and walls, Çatalhöyük with its rooftop streets, Mergar on the road to the Indus cities, Nabta Playa in the Sahara, showing astronomical alignments. These are loud in the archaeological record relative to their populations. If a Holocene-level society had achieved steam, steel, and scale, and then collapsed, we would expect a continental rash of iron slag, brick spreads, canal cuts, mine adits, and alloy residues, the kind of debris we find in profusion from the Bronze and Iron Ages without industry. We don't see that missing century of cogs. Constraint 4. Cross-checks with climate. Agriculture, cities, and deforestation produce regional climate signals. Pollen shifts toward crops and weeds, soot in lake cores, changes in flood frequency, altered fire regimes. These proxies light up in the last few millennia in step with known expansions of farming and states. There isn't a phantom earlier spike in multiple basins that screams global industry, then silence. The climate pages that survive the Holocene show gradual human intensification, not a lost industrial roller coaster. Now widen the lens to other hominins, our cousins and ancestors. Neanderthals sculpt glue from birch bark and twist rope. Denisovans leave a ghost genome and a few enigmatic bones. Homo erectus runs for 1 million years with fire and Acheulean skill. Homo naledi deposits its dead in deep chambers. H. floresiensis and H. luzonensis improvise on islands. This is a chord of intelligence across species, but none show the telltale ratchet to industry. Sustained population growth, surplus accumulation, deep mines, continental trade, metallurgical progression. Their material culture is beautiful, ingenious, and stable on long timescales. Signals of cognitive sophistication without the runaway feedback loop of energy and information that turns a culture into a technosphere. A skeptic might still ask, what if a localized industrial bloom flared and died, small enough to evade global proxies but large enough to be industry in spirit? Imagine a river civilization that stumbles into abundant bitumen seeps, devises pressure vessels, and builds a modest power economy for a few centuries before flood, war, or plague erases it. Could we miss that? Perhaps. Localized industry might leave regional technofossils polymer-like residues if they invented analogs, slag heaps, altered isotopes in a single watershed, a rash of standardized bones from domestication, all without a global bundle. Archaeology has found Bronze Age tin trade webs, Roman concrete harbors, Han ironworks, Mayan waterworks, grand feats that still fall well short of fossil-fueled industry. The nearer we scan a region, the more we find. The absence of a blatant proto-industrial complex across multiple continents argues that, if any such bloom existed, it was rare, brief, and small. The ice ages matter too. For most of the past 2 million years, Earth toggles between cold glacial states and warmer interglacials. Sea level rises and falls by over 100 meters. If cities ever lined a shelf edge during a warm interval, the next glaciation would strand them high and dry or drown them in the following melt. Submerged coastal archaeology is hard but not hopeless. Sonar and cores are revealing paleoriver channels, drowned forests, Mesolithic shore sites. The pattern so far aligns with expected Holocene precursors, fish traps, camps, middens. Not fossil heat engines. If there were iron foundries on Pleistocene coasts, their slag would pepper uplifted terraces and deltaic cutbanks. It doesn't. Then there is time's math. The window in which a pre-Holocene Homo sapiens industry could have arisen with a chance to be preserved is not vast. To leave a global mark, you need centuries of synchronized activity across multiple regions. To erase that mark, you need erosion and burial to outrun discovery for every promising archive. The longer we drill lakes, shelves, and ice, the more confident we become that nothing like our industrial bundle lurks in the last few 100,000 years. That doesn't close the book on deeper time. It narrows the chapter headings. So the human timeline check hands us two essential lessons. Lesson 1. Industry is not just intelligence plus tools. It is dense energy plus scale plus networks plus institutions, a phase change in how a species couples itself to the planet's flows. That combination took Homo sapiens the full run of our species to assemble, and only fully snapped into place in the last few centuries. Expecting it to have appeared, vanished, and left no robust trace within the same species, in the same places we now comb meticulously, asks a lot of coincidence. Lesson 2. Archaeology and geoscience are already finding everything else, from microscopic cut marks to the pigments on Paleolithic walls, from ancient DNA in cave sediments to footprints of children squelching through soft mud. The sensitivity of our instruments and the volume of our discoveries make the non-discovery of a prior human industry into data. It doesn't prove impossibility. It sets upper bounds on how large and how long-lived such a ghost could have been. And yet, humility refuses to die. The fact that we took so long says nothing about what another lineage might have done given a different cognitive architecture, climate rhythm, or catastrophe. The rocks do not know which hands pulled the levers. Our checks conclude only this. If there was an earlier human industry, it was almost certainly small, local, and brief, too modest to register as a planetary event. If there was an earlier non-human industry in deep time, its discoverability will rise and fall with the same conditions we've mapped. Preservation in quiet basins, the existence of synthetic-like residues, and the kind of global synchrony nature hates to imitate. The mirror finishes its work with a question. Our climb required a lucky braid of ice, fire, plants, ores, and stories. We stand on that braid and look back over voids where civilizations might have been. If we want to see farther, we must core deeper and think colder, less like romantics chasing ruins, more like auditors reading ledgers. The young layers where our own entries are fresh have taught us how the columns should add up. Now we turn to meaning, whether or not anyone came before. What does it do to us to realize that the planet forgets almost everything, and that the thing it remembers best about civilizations is not their poems or their palaces, but their chemistry? Geology is a patient storyteller with a brutal editor. It keeps the plot, but cuts the dialogue, compresses chapters into margins, and lets whole characters vanish between pages. Stand at a road cut, and you can feel that ruthlessness. A billion years on the left, pink granite, metamorphic ghosts. A few 100 million in the middle, rippled sandstones. A whisper of an inland sea. A sliver on the right, glacial tills, river gravels, asphalt. We fill our lives with detail. The earth reduces us to a line. That is not an insult. It's a perspective. The Silurian question, could there have been someone before, is really a lesson in scale. Civilizations move fast. Planets move slow. Where we seek statues, Earth offers chemistry. Where we expect cities, it gives us cycles. The humbling part is not that ruins don't last. It's that most things don't. Coral reefs, mountain ranges, entire oceans gone, remade, remembered only as tweaked isotopes and tilted beds. In that company, a species that wires itself around the globe and burns ancient sunlight for a few centuries is an event, not an era. Humility starts with accepting the archive we have. It's biased toward quiet lakes, deep basins, accidentally sealed caves, yet it's also stunning. We can read the breath of forests in trapped bubbles, the ash of long-dead fires in flecks of black, the hunger of past oceans in the thickness of chalk. The rock record is not silence. It's compressed speech. Our job isn't to demand novels where there are only margins. It's to learn the language of margins well enough to hear a civilization if it ever sang. That language is a set of bundles, not monuments. Nature can make soot, carbon dips, metal spikes, even glass beads one at a time, in the wrong order, over the wrong span. Industry, by its nature, stacks them tightly and everywhere at once. When we insist on coincidence in complexity, carbon and nitrogen jolts, combustion spheres, polymer ghosts, alloy-borne minerals, and brief biotic weirdness, we aren't moving the goalposts, we're acknowledging how easily we fool ourselves. Humility is the solvent for wishful thinking. It also works the other way. Humility toward absence. The failure to find a prior global bundle doesn't prove no one came before. It proves that if someone did, they didn't shout in the ways we know how to hear. No worldwide carbon cliff, no synthetic residues in many basins, no policy like on divided by offcuts. Maybe they never reached fossil fuels. Maybe their industry was local and short. Maybe they prospered in a way that didn't require giant furnaces or clever poisons. Humility means keeping that door ajar without letting every draft become a ghost. There's a deeper humility in recognizing that we, too, will be compressed. Our cities are ephemera. Our archives, servers, libraries, films will not survive the teeth of water, heat, and time. What will? Thin pages, a plutonium seam, a soot bloom, polymer residues, a standardized skeleton that turns up everywhere. We are not the sum of our wastes, but our wastes are what stone will keep. That knowledge nudges a moral question. If the future mostly sees our externalities, what do we want those to say? Humility doesn't mean small ambition. It means clear criteria. The same discipline that guards us from false positives can point our searchlights with precision. We can map promising basins, pre-register what counts as industrial, and accept the verdict whether it flatters us or not. A mature civilization is one that can investigate its own uniqueness without needing the answer to be flattering. And there's wonder here, not just caution. The idea that rock holds memory at all, that lakes write diaries, that oceans keep receipts casts our species into a grander chorus. We aren't the authors of Earth's story. We're late arriving, scribes with good instruments. If we find nothing but nature in every candidate layer, we still win. We'll understand our planet better. If we find a genuine technosignature, a thin global cord of impossible chemistry, we'll share the stage. Either outcome enlarges us. Humility also rearranges our sense of time. We tend to treat civilization as inevitable, as though intelligence naturally rises to steer a world. The rock record rebukes that. Life spent billions of years inventing photosynthesis and shells. Intelligence is a younger experiment. Industry, a blink. If civilization is not a default state but a rare phase change, then its detectability is fragile and its responsibilities heavy. The odds that two independent lineages crossed the industrial threshold and left legible global notes may be slim. If we are alone in that feat, the silence is not a triumph but a warning. Systems like ours might be self-limiting unless they learn to quiet their signature without dimming their light. That is the paradox to carry forward. The clearer a civilization's layer, the louder its mistakes. Plastics, fallout, soot. These are the loud parts of our song. A wiser version of us might aim for a different melody. A long, soft line of resilience, energy that doesn't spike isotopes, materials that return to cycles, cities that weather into soils without leaving toxic monuments. Humility asks us to imagine an time's Anthropocene signal that is legible without being a cautionary siren, evidence of agency without evidence of harm. Finally, humility widens the search beyond Earth. The Moon's patient dust, Mars's layered ice, asteroids with suspicious scars all invite the same method. No myths, no ruins worship, just patterns and physics. If we ever read a deliberate line elsewhere, it will be because we learned here to separate desire from data. So we stand before the rock record and accept both its limits and its gifts. It won't hand us certainty. Probabilities, bounds, and the occasional miracle of a clear page. In return, it asks for discipline, patience, and the courage to sit with ambiguity. That bargain is not just good science, it's good civilization. Our next step turns the gaze back on ourselves. If geology remembers our chemistry better than our stories, what obligations follow from that today? While we still get to choose the plot, if the planet mostly remembers chemistry, then our legacy is already under construction, and not by poets. It's being poured, combusted, leached, eroded, and rained out. That realization lands like a mirror. The rock record is not just a place we look for others. It's a place where we are being watched. Look at the line we've drawn so far. It is thin and dazzling. A sudden rise of greenhouse gases, a decline in heavy carbon, a razor of fallout, a blizzard of polymer ghosts, a flood of domesticate bones, and the black confetti of combustion. Behind every data point stands a human choice. We did not stumble into this layer. We engineered it piece by useful piece. We lit cities because darkness was limiting. We mined because stones held stories of power. We farmed intensely because hunger is persuasive. We made plastics because the world is wet and fragile, and polymers are good at ignoring both. None of these decisions is senseless from inside a life. But the ledger doesn't list intentions. The ledger lists effects. This is what the Anthropocene, ratified or not, offers as a moral technology. It lets us see our actions at geologic scale while we still have hands on the controls. We can read, in almost real time, the consequences of habits that feel normal. That's rare for a species. Trilobites didn't get quarterly updates on Cambrian oxygen. Forests didn't get a heads up before the Carboniferous buried their bodies into coal. We do. The line we're making answers when we ask, what will remain of us? And the answer isn't our ambitions or our arguments. It's our inputs and outputs. So what would a responsible layer look like if we decided to write one on purpose? First, it would be long. Not loud, long. Loud layers are spikes. Brief, bright, and often catastrophic for somebody. A long layer is a soft, steady pattern that learns how to stay interesting without breaking things. In chemistry, that means energy sources that don't yank the carbon cycle by the collar, materials that return to their elements without leaving synthetics lodged like sand in the planet's gills, and nutrient loops that treat nitrogen and phosphorus like precious, recirculating script instead of confetti. Second, it would be reversible where possible and bounded where not. If we must make polymers, we make ones that fall back into biology on tolerable timescales. If we must use rare metals, we build infrastructures that recapture them, the way rivers recapture silt, until the rare is mostly in circulation, not in holes in the ground. Where irreversibility is real, species lost, Ice melted beyond glacial thresholds, we treat it as a sacred cost and design our lives to avoid paying it. Third, it would contain legible signals of restraint. The rock record already registers our policies. The sudden bend in lead after the end of leaded gasoline, the clipped fallout curve after the test ban, the sulfate shift after air quality laws. A responsible civilization would leave patterns that look like intention rather than accident. Abrupt plateaus in atmospheric curves when a treaty bites, synchronized declines in waste residues after circular economy designs take root. The rise of new minerals that are designed to be temporary. To a future geologist, restraint would look like a series of gentle corrections, course changes too fast for orbital mechanics, too coordinated for volcanoes. Fourth, it would be quietly abundant. The goal isn't to vanish from the record, it's to replace catastrophic markers with benign ones. Imagine a thin horizon of engineered stones that dissolve back into limestone and clay, of pigments that fade into iron oxides and carbon blacks, already common in soils of cities whose demolition rubble is quarry feedstock for their grandchildren's homes. Imagine bones that tell a story not of a few hyperabundant domesticate morphs, but of rebuilt diversity, reconnected habitats, migration corridors that let hoof and wing redraw their old, pre-human maps. Biodiversity recovered is a stratigraphic signal too. It changes pollen profiles, biomarker ratios, even the grain size of sediments when rivers run through living banks. None of this is mysticism. It's engineering and governance choices that scale. And the rock record is not patient with our excuses. It is a scoreboard that cannot be spun. You can negotiate a press release. You can't negotiate a delta to the power of 13C curve. What does this demand from us now, inside lives that don't feel geologic at all? It asks that we stop treating the future stratigrapher as a ghost. When we design a product, a port, a policy, we can ask the rock's question: what fraction of this will still be legible as harm in 1,000 years? If the answer is most, we have not yet designed well. When we pick energy infrastructure, we can ask, will this choice write a spike or a line? If the answer is a spike, we haven't yet been serious. It asks that we reframe growth. The kind that draws steep, short lines in cores is often the kind that treats externalities as invisible. The growth worth bragging about is the kind that leaves integrated layers, prosperity without poison, longevity without loudness, complexity that composts. We already know how to measure this, not just in GDP, but in tons of material recirculated, in watts delivered with carbon neutrality, in hectares rewilded, and in pollutants, declining so fast that even a varved lake can feel the policy. It asks for memory, because the rock record teaches the opposite of complacency. It says the world forgets almost everything. That means our institutions must remember what stone won't: stories, crimes, recoveries, lessons. We build cultural strata on top of geologic ones, legal traditions that outlast lifetimes, education that inoculates against our own pattern hunger, archives built with redundancy and renewal so that data survive formats and regimes. The rock doesn't keep libraries. We must. And, maybe most practically, it asks for honest thresholds. There are lines that, once crossed, leave signatures no treaty can erase: ice sheet collapse, mass extinction pulses, runaway nutrient loops. Our responsibility is to decide, in language plain enough to audit, which thresholds we will not cross, and then design markets, technologies, and enforcement that make those vows real. The rock rewards clarity. It punishes delay. When people talk about legacy, they tend to mean names on buildings or ideas in books. The Silurian lens, this forensic way of seeing, offers a sterner meaning. Legacy is the shape of your layer. Is it a spike with a siren? A smear of damage fading into silence? Or a long, low hum that supports other life and leaves the next readers a planet with options? We may never learn whether we share this planet with the ghosts of a vanished industry, but we can decide whether any future minds, human or not, will look back at our thin seam and see hubris or wisdom. That choice is not abstract. It is material. It's cement chemistries and power grids, crop rotations and trade law, urban planning and cultural taste. It is also, finally, a story because the will to change comes from meaning as much as from metrics. Kind, because it reminds us that we are not condemned to be loud. Severe, because it shows how much of our noise is optional. We can write a layer that reads as care. What if we're not the first? Maybe somewhere, long before us, hands will never meet. Learned how to turn stone into power and darkness into day. Maybe they wrote their best ideas in materials that the planet doesn't keep. Maybe their cities stood for centuries. Their maps were exquisite, their music perfect, and then plate tectonics filed them under miscellaneous, the way it files most things. Maybe not. Maybe the silence is the truth. Maybe intelligence rarely crosses the narrow bridge to industry, and we are a singular experiment, brilliant, fragile, and unrepeatable for a million lifetimes. Either way, the rock record leaves us with a choice more urgent than the mystery. If civilizations are flashes in a deep night, then the measure of wisdom is not how brightly we flare. It's how long we can keep the light without burning the house. The planet will forget our stories. It will remember our chemistry. The question waiting at the end of this investigation is not, were they here? But what will they learn about us when they read our thin seam? Stand with me at that road cut one last time. Run your fingers across the layers, ripple marks frozen mid-wave, a volcanic ash that tastes faintly of sulfur, a brown band of ancient soil. Then feel the youngest sliver, a dusting of soot, a whisper of plastics, a breath of plutonium, the faint geometry of bones made in factories of flesh. That is our paragraph in Earth's book. We are still writing it. If we want the next reader, whoever they are, whenever they wake to find more than a cautionary spike, we have to change the plot while the ink is wet, build energy that doesn't yank the carbon page, make materials that know how to say goodbye, treat rivers and soils like they're the memory of the world, because they are. Put restraint into law and design it into habit. Leave room for wildness to write its own lines again. And keep looking. Drill where time stacks thin and clean. Audit the margins. If a thin chorus of impossible signals ever rises from ancient mud, meet it with the seriousness it deserves. It might be the oldest conversation in the world. Two brief flames, separated by millions of years, recognizing each other by the way they stained the air. What if we're not the first? It is a question that invites wonder and discipline in equal amounts. But the answer that matters most is the one we can still shape. When our page is pressed flat and the rest of our story is lost, will the layer that bears our name read as warning or as care? If civilization is a momentary flame, carbon is the smoke it leaves behind. Combust an industrial world and you don't just warm the air, you rewrite the chemistry of the planet's reservoirs. Fossil fuels are ancient sunshine distilled into carbon chains and rings. When we burn them, we inject that very old carbon back into the sky and sea. Crucially, that carbon carries a telltale isotopic accent. It's light depleted in carbon-1,3, nom-ku, relative to carbon-1,2, non-squared-C, because plants prefer the lighter isotope, And fossil fuels are just ancient plants under pressure. Pour enough of that light carbon into the system quickly, and the entire planet's carbon ledger ticks downward in a sharp negative carbon isotope excursion, CIE. That's not. We know this pattern intimately because we're living it. Since the Industrial Revolution, delta to the power of 13C in atmospheric CO2 and in carbonate archives has trended lighter. A global signature now echoed in lakes, marine sediments, and even tree rings. It's the isotope equivalent of catching a suspect on camera. But in deep time, cameras are rare and grainy. Single clues can mislead because nature runs its own experiments. Massive volcanic provinces can belch carbon, seafloor clathrates can belch methane, peatlands can burn. All can push delta to the power of 13C downward. So how do we tell industry from geology? The answer isn't one line, it's a bundle. The Silurian Hypothesis explicitly argues for a suite of tests. Combine isotope anomalies with other fingerprints materials, radionuclides, sediment changes, biosphere shifts, and demand planet-wide synchrony on tight time scales. To see how this works, consider Earth's most famous ancient CIE, the Paleocene-Eocene thermal maximum on PETM, to 56 million years ago. In a geological heartbeat, global temperatures jumped roughly 5–6 degrees Celsius. The oceans acidified, and delta to the power of 13C plunged textbook features that echo our modern trajectory. The PETM is a perfect foil for our search. It's dramatic, global, and natural. High-resolution work continues to refine its tempo, but even updated astrochronologies and new proxies point to an onset that, while geologically fast, likely unfolded over thousands of years, slower than our modern carbon shock by orders of magnitude. That difference in rate, plus the absence so far of unmistakably synthetic co-markers, is why PETM remains a natural hyperthermal rather than our smoking gun. It teaches us what an intense non-industrial carbon dump looks like, so we can recognize when something stranger appears. Speed matters because the carbon cycle is a system with buffers. Add carbon slowly, and oceans and minerals partially cushion the blow. Add it explosively, and those buffers lag, leaving a sharper isotopic cliff and more severe acidification over shorter intervals. Our contemporary pulse is an unprecedented geological sprint, a reason the Anthropocene's isotopic contour looks razor-edged in varved lakes and rapidly accumulating sediments. If a prior industry ever flared and vanished, we'd expect something similar. A compressed, global CIE with flanking anomalies that resist purely volcanic or biogenic explanations. Carbon isn't the only isotope ledger civilizations scribble in. Nitrogen carries its own telltales. Industrial fixation, Haber-Bosch, and fossil fuel combustion have tripled the amount of reactive nitrogen humans shuttle through air, soils, and waters. That upheaval shows up as shifting delta to the power of 15N values in nitrates preserved in ice and sediments, a long, coherent signal beginning in the 19th century and sharpening through the 20th. In many records, delta to the power of 15N trends lighter, consistent with the influx of isotopically distinctive human-made nitrogen sources. In a hypothetical deep-time industry, you'd look for a coincident nitrogen cycle disturbance, altered delta to the power of 15N in the same thin horizon that shows a carbon jolt, because nothing in nature routinely rearranges both the carbon and nitrogen cycles globally within centuries. Now, add radiocarbon, 9-quadruped Z, the clock built by cosmic rays. Burning fossil fuels dilutes atmospheric Buenforted C with dead carbon, a century-scale wiggle called the Suis effect. Mid-20th century nuclear tests briefly reversed that with a spike of bomb-Buenforted C. In our own layer, those two moves, dilution by fossil carbon and a pulse of artificial Dumu-ported C stack, like a signature pair of fingerprints. A prior civilization might not split atoms the way we did. But if it did, its Dumu-ported C anomaly would be an elegant timestamp. And even if their technology took a different path, the fossil carbon dilution alone, if intense and rapid, would leave a recognizable radiocarbon distortion nestled inside the broader carbon isotope fall. In our time, bomb.microt's razor line is cross-checked against plutonium and cesium to lock the date. Isotopes do more than memorialize chemistry. They map ecology. When you flood the system with CO2 and nutrients, ecosystems reconfigure. Ocean acidification thins or dissolves carbonate shells. Food webs shuffle. On land, fertilization and warming pick ecological winners and losers. Those shifts are recorded in the isotopic values of organic matter, in the carbonate of shells and soils, and in the ratio of different biomarkers. If you found a narrow horizon where delta to the power of 13C plunges, delta to the power of 15N tilts, carbonate preservation falters, and biological markers flip in concert, and if that horizon coincides with other industrial hints, unusual metals, synthetic residues, you'd have the beginning of a technosignature case. That's exactly the style of multi-proxy logic proposed by the Silurian framework. Stack independent lines until natural alternatives become improbable. Skeptics will ask the right question. Couldn't massive volcanism mimic much of this? Indeed, large igneous provinces can inject both CO2 and toxic metals, drive warming, acidify oceans, and dust the planet with glass and ash. That's why single proxy arguments fail. LIPs leave petrological footprints, basalts, distinct ash chemistries, sulfur isotope behaviors, and time-integrated patterns of weathering that differ from an industrial surge concentrated in a few centuries. Likewise, methane clathrate releases push delta to the power of 13C, even lighter than CO2, but should carry distinctive stratigraphic fingerprints, for example, carbonate dissolution patterns, without attendant synthetic residues. Parsing these differences requires global cores, precise dating, and a willingness to pit our favorite stories against stubborn numbers. The advantage we have now, thanks to Anthropocene studies, is a template of what an industrial pulse definitively looks like, down to annual laminations in some lakes. Where then should we expect isotope clues to survive? Not on mountain flanks or surf-chewed coasts, but in quiet archives, anoxic basins, rapidly accumulating continental shelves, deep sea ooze that escape subduction long enough to be uplifted into tomorrow's outcrops. In those places, thin time is preserved. At Crawford Lake, for instance, you can track the mid-20th century page break almost year by year. The arrival of plutonium, the shift in carbon and nitrogen proxies, the micro-ash of combustion. That coherence is what we'd need to see in ancient sections to whisper industry. Finally, a practical test the Silurian paper suggests between the lines. Look for coincidence at global scale. It's one thing to find a weird isotopic dip in a single basin. It's another to map the same sharp excursion, with similar timing, across continents and oceans, then watch it travel with a companion suite: metals, synthetic like organics, fallout markers. The more co-registered those curves are, the less room nature has to impersonate us. The hunt, then, is not for a lone smoking layer but for a chorus. Delta to the power of 13C, delta to the power of 15N, radiocarbon quirks, carbonate dissolution, a biomarker flips, singing the same brief, dissonant note around the world. If we're not the first, carbon and nitrogen are likely the first whisperers to tell us so. A fast, light-leaning breath in the rock record, too quick for volcanoes, too global for local fires, too bundled to be chance. And if we are the first, those same ledgers will one day be our biography in stone. Our brief argument with the atmosphere, written in ratios and decimals, waiting for someone else's drill. If isotopes are the whispers, materials are the teeth marks, physical scars that don't care whether a storyteller survives to explain them. Start with the strangest candidate: plastics. They're everywhere precisely because nature never evolved a tidy appetite for them. Sunlight brittles them, waves abrade them, microbes nibble at the edges, but the family persists. Large pieces grind down into confetti, then into fibers, and fragments so small they drift like pollen. In sediments, those flecks can become part of the matrix, tangled with clays, glued by biofilms, tucked into pores, eventually sealed under new layers. Over geologic time, some will deform, some will cross-link, some will carbonize, but a fraction will fossilize as polymer ghosts, odd organic residues and shapes that don't match known biopolymers. Imagine a shale that, under a microscope, holds tiny angular shards and threads with uniform chemistries not seen in nature's catalog. That's not mythology. That's a potential technofossil. Then there's concrete, our domesticated rock. On day 1, it's a paste. By day 28, it's a stone with its own minerals: calcium silicate hydrates, ettringite, portlandite, buried, fractured, and hydrothermally altered. Concrete keeps evolving, recrystallizing into sweets you don't find in untouched limestones or volcanic tuffs. Add steel reinforcement and you get corrosion halos. Iron oxides bleeding into the surrounding material in radial patterns that betray a grid-like origin long after the bars themselves are gone. Time can turn a bridge into rubble and rubble into breccia, but its chemistry stays off. In cross-section, a future geologist might see rubble layers with angular clasts of cement-bound aggregate, glass, brick, rebar stain streaks, an urban conglomerate unmistakably unlike river gravels. Glass becomes a chronicle too. We make it unnaturally pure and flat. We make foams and fibers and tempered panes with characteristic stress patterns. We fuse silica with metals for screens. We leave behind thick blankets of microbeads from blasting and polishing, buried in the right place, say. Beneath an old city landfill overlain by flood sediments, glass will devitrify slowly, developing textures that still betray an industrial origin. Bubble trains trace metal fingerprints. Laminar flows frozen at human scales. Volcanic glass exists, yes, but it carries its own chemistry and vesicle habits. Window glass and smartphone glass are not obsidian. Their stories are different, and that difference can survive time. Pure aluminum is rare in nature. So are some stainless compositions and high-temperature superalloys. In the short term, they corrode. In the long term, they become mineralogical evidence. Oxides, hydroxides, and exotic secondary minerals forming from compositions that never appear in untouched ores. If these appear in a layer with global distribution, say, across multiple basins and continents, it hints at large-scale smelting and dispersal rather than a local oddity. Trace element ratios can whisper process. 2. The fingerprint of ore refining. The telltale association of rare earths, from e-waste, the odd co-presence of gallium, indium, and tin that makes sense in a world of LEDs, photovoltaics, and solder, but not in ordinary rock. Even carbon itself takes on industrial forms that nature seldom crafts in bulk. Think spheroidal carbonaceous particles from high temperature, combustion glass-shelled, glossy black microspheres born in flames controlled by chimneys and turbines. They rain out widely and slot into sediments as a black confetti distinct from wildfire charcoal. Microscopy can sort them by shape and luster. Chemistry can sort them by origin. If you find a narrow stratum, global in reach, where such particles bloom in concert with other oddities, you found a page with human handwriting. Biology writes along the margins. Our civilization's bone layer is bizarre. Billions upon billions of domesticates with convergent body plans, broiler chickens, feedlot cattle, standardized pigs piled into landfills and lagoons, flushed into river deltas during floods, scattered as incidental fossils far from any natural habitat. Over geologic time, most will vanish. Some will mineralize. To a patient future paleontologist, that sudden global arrival of anatomically uniform, rapidly growing morphs appearing everywhere at once and then stabilizing or collapsing will look nothing like a slow evolutionary radiation. It will look like manufacture with biology as the medium. The built environment also creates rock types that don't quite fit any pre-industrial analog. Asphalted surfaces become dense, hydrocarbon-rich layers. Synthetic foams and insulations leave behind curious void textures. Pigments dot grains with titanium dioxide and artificial blues and greens. Landfills, capped and compacted, become strange composite hills with metal-rich leachate halos and methane chimneys that over time cement into peculiar cements. Mines invert mountains, concentrating tailings into engineered strata rich in sulfides that oxidize and then reprecipitate into gaudy secondary minerals. Cities are, in a very literal sense, mineral factories. When they fall apart, the factory keeps running underground. Consider also the global distribution of these technofossils. Natural processes are patterned by climate and geology. Deserts leave aeolian, sandstones. Deep seas leave chalk and ooze. Volcanoes leave ash with specific fingerprints. Our distribution is driven by supply chains and markets. Polymers washing up on both Arctic beaches and tropical mangroves. Fly ash sprinkled over continents according to wind belts of a particular century. Concrete rubble packed thickest at coastlines where megacities cluster. That human logic trade routes, population density, energy corridors, translates into geologic logic, a geographic coherence that makes little sense in purely natural models. If another industry once spanned the planet, its wastes would also scatter according to whatever physics and economics governed it. We should expect not just odd materials, but odd maps. What about time compression? A civilization scale layer is thin. In lakes that lay down laminations you can count like tree rings. Our technofossils compress into millimeters. On continental shelves with faster sedimentation, you might get centimeters. Inland, on floodplains and deltas, they'll intermix with storm pulses and drought hiatuses, still recognizable as a discrete chapter if you zoom out. In the open ocean, the signal dilutes into a whisper, but can still be teased out with careful chemistry. The point is not that technofossils build grand monuments, they build bundles. A set of industrial crumbs that, taken together, corner you into admitting agency. Skeptics will ask, couldn't nature mimic some of these? Yes, bits and pieces. Volcanic glass exists. Wildfire charcoal exists. Orthogenic cements are common. But the coincidence of so many independent markers, plastics or polymer residues, industrial glass, engineered concretes, alloy-derived oxides, combustion microspheres, domesticate bone floods stacked in a tight window and repeated across many sites, is the giveaway. Nature can fake a signature. Faking a chorus is harder. There's also a philosophical comfort in materials. They collapse the distance between civilization and geology. We like to imagine ourselves as apart from stone. In practice, we are authors of a new lithology. If some earlier species reached for industry, they would have discovered the same stubborn truths. That it's easier to pour lime than carve granite. That alloys beat ores. That mass production leaves a sedimentary footprint you can't completely erase. If they researched, mined, built, and discarded at global scale, their passage through time would be written in things not as museums, but as mineralized habits. So the checklist we carry forward looks like this. Search quiet, well-dated archives for thin intervals where materials get weird on every front at once. Look for polymeric residues and fibers entombed in clays, for urban conglomerates and concrete-derived cements, for fly ash spheres and unusual glass, for alloy-borne oxides and rare earth anomalies, for a sudden, planet-wide surge of standardized bones. If you can map that bundle from lake beds to shelf muds to uplifted marine rocks on multiple continents, you've taken a step beyond curiosity into evidence. If a pre-human industry ever existed, its ruins are long gone, but its habits, what it made, used, and threw away, may still be there, pressed into stone, waiting for a microscope and a question bold enough to ask. If technofossils are the crumbs, radionuclides are the timestamp. The razor-thin line that says not just something happened, but exactly when. Mid-20th century humanity briefly sprinkled the entire planet with atoms that nature almost never scatters on its own. Above-ground nuclear tests lofted plumes into the stratosphere, which then circled the globe and snowed out as a synchronized haze of artificial isotopes, plutonium-239 and -240, cesium-137, americium-241, and a spike in radiocarbon, Vunkwarted-C, known as the bomb pulse. These aren't rumors. They're measurable, datable, and already used as stratigraphic guideposts. Consider plutonium-239. With a half-life of about 24,110 years, it outlives empires and ice ages, lingering long enough to stencil a crisp horizon in sediments and ice for tens of thousands of years. Its cousin Pu-240 half-life to 6,560 years rides along, and the characteristic Pu-isotope ratios from weapons fallout help distinguish it from other sources. Together they form a durable, globally synchronous tracer of the Great Acceleration, years when industry and population curves went vertical. If you want to see that page break, open a core from Crawford Lake in Ontario, the same quiet, laminated basin scientists nominated as a golden spike candidate for our age. Year by year, VARVs, they record the first appearance of plutonium and other bomb-era radionuclides. In the early 1,950 seconds, peaking around the early 60 seconds, an almost cinematic cut in the rock record. Whether or not Anthropocene epoch is formally ratified, the plutonium line in Crawford's mud is unambiguous, and it's the sort of planetary timestamp we'd hope to find in some ancient guise. If anyone came before, cesium-137 tells the same story with a different voice. With a 230-year half-life, it lights up the mid-20th century and then fades on human timescales. perfect for pinning layers to specific decades. It has been mapped from lakes and estuaries to continental shelves and open ocean muds. Because accidents like Chernobyl added regional WQBD seas on top of global weapons fallout, researchers can even use paired plutonium divided by cesium measurements to separate global bomb signals from local or regional releases. Another reason the bomb horizon is so diagnostically clean. Then there's the Dunwachert-C bomb pulse. A spike in atmospheric radiocarbon caused by neutron bombardment of nitrogen during weapons tests, roughly doubling atmospheric PUN IOC in the early 1960 seconds before treaties pushed tests underground. That pulse propagated through every living thing, from tree rings to human tissues, and is now used as a forensic chronometer to date material formed in those years with uncanny precision. In sediments and corals, the rise and decline of bombed Dunwachert-C draws a distinctive curve, cross-checking the plutonium and cesium clocks. Why did this global line appear so sharply? Policy. Ironically, the 1963 Limited Partial Test Ban Treaty halted tests in the atmosphere, space, and oceans, cutting off the source of fresh fallout and pinning a near-instant end to the bomb-era deposition. The result is a stratigrapher's dream, a narrow planet-wide layer bracketing the late 1950 seconds to early 1960 seconds. Even with later incidents and underground tests, the atmospheric on divided by off switch of 1963 keeps the primary signal neat. For our investigation, the significance is twofold. It proves the concept. A technological civilization can, in fact, imprint a global, synchronous chemical line that persists for geologic spans. If you found an ancient horizon with unusual, non-natural radionuclides, or a statistically bizarre arrangement of long-lived isotopes coherent across continents, that would be an extraordinary hint of industry. We don't expect PU 239 specifically from a non-human past. We expect the analog, artificial radionuclides, or isotopic cocktails that nature rarely makes and almost never distributes globally in a tight window. It shows how to separate signals. Stratigraphers already disentangle global weapons fallout from regional accident plumes using isotope ratios and co-occurring markers. The same logic applies backward in time. If you encountered a thin horizon rich in odd isotopes or activation products, you would ask, is there a natural mechanism? Large igneous provinces, cosmic ray anomalies, meteor impacts that could create this mixture and spread it worldwide on century timescales. Failing that, you'd look for the bundle: metals, technofossils, combustion particles, and biosphere shifts riding alongside the radionuclide anomaly. A skeptic might counter, nature does mess with radioisotopes, cosmic rays make Innungforters see, volcanoes and impacts can loft dust worldwide, and uranium series daughters appear in many settings. True, but the combination is the key. Weapons-era fallout is global and weird. Isotopes with half-lives and ratios that point to human nuclear reactions, spiking nearly simultaneously across the planet, then tapering after 1,963 inches lockstep with treaties that shape rapid onset, planet-wide coherence, policy-driven cutoff, is profoundly unlike the smeared, multi-millennial signatures left by natural processes. Zoom back to method. In practical field terms, the search for ancient technosignatures would prioritize quiet, continuously layered archives, varved lakes, anoxic marine basins, and carbonate-forming settings, because that's where thin time is preserved and where radionuclide horizons resolve cleanly. We'd assay cores for long-lived, non-naturally co-occurring isotopes, map their appearance across a global transect, and check for the industrial chorus nearby. Spikes in combustion microspheres, polymer residues, alloy-derived oxides, and synchronized isotope excursions in carbon and nitrogen. If those curves all sing the same brief note, we have more than a curiosity, we have a case. And if nothing like it exists in deep time, then our fallout line becomes something else. A mirror. It's the thinnest of layers, millimeters of mud, yet it shouts agency across the planet. Whether or not anyone preceded us, this luminous seam of human-made atoms will be legible to future geologists and, perhaps, to future civilizations. If someone, someday, asks of us what we're asking of the past, were they here, the radionuclides will answer first.